second session of the workshop. My name is Eric Koch from Forschungszentrum Jülich, and I'm going to chair this session. And we start with a talk by Massimiliano Stengel from Barcelona, and he's going to talk about flexoelectricity.
Yes. Flexoelectricity is hidden in the title, but I promise I'll talk about flexoelectricity. So thanks for the introduction. Thanks to the organizers for inviting me here. It's always a pleasure to come back to San Sebastian. So the title is a little bit different from what you see in the abstract book, but it's about the same. So I decided to focus more on the latest developments rather than give you the usual old talk about flexoelectricity that I gave many times. And this is more general about spatial dispersion properties that include flexoelectricity but are not limited to it. These are the main collaborators for this work. Miquel Royo has done an excellent work by implementing all the theory I'll be presenting to you later. He's a postdoc in my group. Andrea Schiaffino did part of the work. He's been a student, a PhD student in my group. He's just finished this summer. Unfortunately, he didn't stick to science. He decided to try the private sector. Let's hope he comes back because he's really good. And then Cyrus Dreyer. He's currently at Stony Brook, and David Vanderbilt, that all of you know very well. So, spatial dispersion, let me start from the title. It describes essentially a physical property of a material that depends on the gradient of an applied field. For example, you don't apply a uniform electric field, you apply a gradient of an electric field and you get something out of it that may differ from the property that emerges from the uniform field. In reciprocal space, this can be written as the Q dependence, as the wave vector dependence of some response function to some modulated perturbation. And the physical origin of spatial dispersion, as you might know very well, is that the response of the materials is non-local. A field applied at a point R always produces a response that is not limited to a delta function on R, but actually affects an area surrounding the point where the field is applied. But this non-locality tends to be quite microscopic in the sense that usually it disappears once you look at the response over a few interatomic distances. So macroscopically, the manifestation of non-locality will be small effects in general, and are well described by some perturbative expansion as in the wave vector Q. Classical examples of spatial dispersion are, of course, the optical response. You can write a sigma that depends on Q and omega, and you can do an expansion in Q, and the various terms in Q are the macroscopic optical conductivity, of course, and then at higher orders, you can have effects like the magnetoelectric coupling or the natural optical activity. And then you have other effects, like in elasticity, the so-called acoustical activity. You must trust me on this, because this is the only formula that didn't came through when importing the file on this computer. But is essentially the same as here, only the zero order is the elastic tensor, and then at first order in Q, you have the dispersion of the elastic tensor, which is the acoustical activity tensor. But in this talk, I will mostly focus on the dispersion of the electromechanical response in materials. And the most obvious example of electromechanical response is, as you all know, piezoelectricity, which describes the macroscopic polarization response of a material to an applied uniform strain. This is described by a third-rank tensor, alpha, beta, and gamma, and since it's an odd rank tensor, it requires a material that breaks inversion symmetry at the level of the crystalline lattice, and relatively few materials display this effect. And of course, there is quite an important search from the point of view of technology to find new piezoelectric materials or materials that have an electromechanical response. And there has been a lot of interest lately on flexoelectricity, which is very much like piezoelectricity, but now the perturbation is not a uniform strain, but is the first gradient of the strain. So instead of doing a compression or a tensile deformation of the slab, I can bend it, for example, and this produces a gradient of the strain. This seems to be out of battery, but it's okay. Anyway, why flexoelectricity? So it is the polarization response to a strain gradient, and you see now it is a fourth-rank tensor, and actually you can, it is a universal property of all materials, so you don't require a special crystalline lattice for flexoelectricity to happen, but you have it in every compound, just even silicon or cubic strontium titanate or any material you can think of. It has been it hasn't been very searched for many years, so it was discovered in the late 60s, but for many years it was a bit neglected, just because at the macroscopic level flexoelectricity is really negligible. You can think of bending a macroscopic slab and you can't go very far, and this means that there's only so much polarization you can get out of a macroscopic object. But at the nanoscale, strain gradients can be huge and actually can produce some interesting physics, measurable and also potentially useful for applications. So what kind of applications are we interested in? Of course, as I said, we can make a replacement for piezoelectrics, for example, by devising some composite where inversion symmetry is broken at the level of the sample shape rather than at the level of the crystalline lattice. You can even use mechanical stress to write information, to write electrical information, for example, on a ferroelectric thin film, where a domain switching was achieved just by pressing with the tip. Flexoelectricity has been invoked to explain a wealth of phenomena. Lately, it has become quite a popular topic. For example, it is believed to enhance the photovoltaic activity. And also there are some demonstrations of how it could be used for practical applications. But from my point of view, from a theoretician point of view, there is a strong fundamental interest in flexoelectricity. First, because it is complicated to describe and calculate, and it involves a lot of different topics in condensed matter to do it well. And also, it is quite nice to study curvature effects on material properties, and that can lead to interesting physics. So the question is how to calculate this fourth-rank tensor with about 54 independent components from first principles. And you can see right away that there is a fundamental problem with it, in that the perturbation is not a homogeneous perturbation, so you can't really just take your unit cell, apply some kind of atomic displacement, or apply an external field and get the answer right away. So the fact that translational symmetry is broken is pretty serious because we cannot use periodic boundary conditions in principle. Bloch theorem breaks down, plane waves as well, and so it seems like we are stuck, but actually there is indeed a way around by using density functional perturbation theory and by modulating, instead of taking a macroscopic translational symmetry breaking perturbation, we just modulate it in a wave, in an elastic wave, which leads us to acoustic phonons. And if you take a snapshot of an acoustic phonon, a longitudinal one or a transverse one, you can see indeed that one recognizes immediately the pattern associated with a longitudinal strain gradient here, or of a shear strain gradient, which is a spatial gradient of the shear strain along the propagation direction. So acoustic phonons can give us the information we need. We just need to know now what to do with acoustic phonons, and this is the main subject of my talk. Essentially, this is the basic summary of what we do. The first thing is to use density functional theory to calculate the polarization response at small but finite wave vectors q to an acoustic phonon. And this includes electronic and lattice-mediated responses. And then the second thing is to actually choose the wave vector of the phonon sufficiently close to gamma so that we can do a Taylor expansion around the gamma point, a long wave expansion, as it is called, and extract the required properties by writing a Taylor series in Q. And here, if I expand the polarization associated with the acoustic phonon in Q, I get three well-known properties. At zero order in Q, I get nothing, just because of the acoustic sum rule that we know since the 50s, I guess, or even earlier. At first order in Q, we get the piezoelectric tensor, and at second order in Q, finally, we get the bulk flexoelectric tensor. So, neither one or two existed before this work, and we had to solve quite a few fundamental and technical issues in order to be able to do that. Essentially, every word you see in these boxes is a technical issue and was not clear how to do it before I started. So I'll just give you an overview of the main difficulties we had to solve and try to sketch a little bit the solution in a way that some physics might emerge in the middle of the formulas. So the first fundamental problem we have to face is to define what is the polarization response to an inhomogeneous perturbation, which in this case is a phonon, but can be any kind of perturbation, an electric field, a vector potential field, or whatever. As I said, there are lattice-mediated contributions, and these are, in the case of the phonon, these are are relatively easy to understand because we just need to know where the atom goes when I generate a modulated phonon at finite Q, and then we have a simple coupling to the polarization, which is given by the Born charges, and this is fairly simple because working with atoms is relatively, intuitively quite straightforward. Things start to become complicated when we are seeking the electronic response to a strain gradient. Just because electrons are not as nice as atoms, so an atomic displacement is an arrow that I can translate into a polarization quite easily, but the electrons is a cloud. And to know what is the polarization determined by electrons, I need to do actually adiabatic perturbation theory, so I need to take an atomic velocity instead of an atomic displacement and see what is the current that flows during this evolution of the system. And this is what I'll focus in most of my talk, which is the main technical problem associated with the calculation of dispersion properties. So the main thing is that the main issue here, when we have an inhomogeneous perturbation, is that this is not a truly macroscopic thing. So we need actually the microscopic current density response to the perturbation, which is not obvious how to get it out of the known formulas, like the Berry phase, for example. So this was the first thing to solve. And one can naively say that we know actually in quantum mechanics what is the current density, and is precisely given by the textbook probability current. However, there are some subtleties here, because this expression does not work when you have non-local pseudopotentials. This is sort of well known in the NMR community. There has been some work many years ago by Pickard and Maury, for example, trying to devise a definition of the current density and then of the magnetization in presence of non-local pseudopotentials. So we actually revisited this problem with the goal of devising a solution that is good for our scopes, which is flexoelectricity in this case. We didn't find really a unique solution to this question, but we found, let's say, a good enough solution to our scopes, which is reasonable and works well. So, of course, we want to do it in the context of density functional perturbation theory. And this is just an overview of density functional perturbation theory for those of you who are not familiar with it. I simply take an expansion as a function of some parameter. We have an Hamiltonian that depends on some parameter lambda. And here I just expanded in powers of lambda the external potential V. Then I have a response in terms of wave functions and energy, which can also be expanded in terms of lambda. At first order in lambda, the energy it looks like are gradients of the ground state energy, and via the Hellman-Feynman theorem, this is easy to compute. If I want to go to second order, which is what I need for the calculation of the polarization, then I need a further ingredient, which is the first order wave functions, which are given by a Sternheimer equation, as you know very well. These are band projectors. So to do it, to use these formulas of density functional perturbation theory, of course, we need to write the polarization response as a second derivative of the Kohn-Sham energy. And this is what I have written here. So the polarization response to some lambda of Q is just the second derivative with respect to the electric field and lambda by using the thermodynamic relationship between the polarization and the electric field. And then we get quite a simple formula for the polarization response at fine Q, which is a generalization of the uniform case. And apart from an integration of the Brillouin zone and a summation over the bands and some factors, is actually a sort of Berry curvature that involves two first-order wave functions. One is the first-order response to a vector potential, to a modulated vector potential. And the reason why the vector potentials appear here is that I define the electric field as the time derivative of A. I cannot apply directly an A in a first principles calculation, like I cannot apply directly. So either I apply a scalar potential or a vector potential. In this case, the vector potential is better suited to our scopes. And then on the other side, I have the first order wave functions, the simple phonon response that is already implemented in Abinit. So this, as I said, generalizes the usual formula for the polarization response in that if you take the Q equals 0 case, you can see trivially that this reduces to the known formulas because the response to a uniform vector potential is just a derivative in K space of the ground state wave function as a purely geometric object. So, I talked about the polarization side, but now we need to take care of the acoustic phonon side, and we need to know what is the perturbation that we apply and how we deal with it. Of course, an acoustic phonon is a phonon, so the simplest approach would be to just take the phonon that is implemented in Abinit, do a summation over the sublattices, and be happy with that. But actually, it turns out that it is much more convenient to do on top of the summation over the sublattices, which is a displacement of the atoms with respect to a fixed laboratory frame, to do on top of it a coordinate transformation of space to the co-moving frame of the elastic wave. So an elastic wave, you can think of it as a transformation from R3 to R3, and why not following with the coordinates, real space coordinates, this transformation in a way that the atoms do not move. And this way, by doing some derivations that I don't have time to present here, we get two very nice properties of this new metric wave perturbation, which is essentially an acoustic phonon in the curvilinear frame, that at q equals 0, the perturbation vanishes exactly, just because the translation, well, nothing changes essentially if you think the atoms don't move, because the frame is moving with the atoms. And at first order in Q, we exactly recover the uniform strain perturbation as was proposed and implemented in Abinit by Don Hamann. So we get 0 and recognizable pieces at the lowest order in Q, and so we are happy with that because it allows us to write a theory of flexoelectricity in terms of already existing ingredients that are already present in Abinit and minimize the coding burden. So let's go back to the clamped ion flexoelectric tensor. As I said, we only have electrons here. This is the, the response function that I described in the previous 2 slides ago, the macroscopic polarization associated with the acoustic wave, which was written as this sort of Berry curvature. I need to take the second derivative in Q, and now I will... So there are several ways of taking the second derivative in Q. We can do it numerically, but it's nice to do the whole thing. So do it analytically and get to some closed formula directly for the flexoelectric coefficient. And if I derive this thing, actually it's... I'll just leave it here. If I derive this formula, I get essentially 2 objects that are of this type. Here, I have the wave function response to the gradient of an A field, which is written in terms of the second derivative in K of the wave functions plus the orbital B response of the wave functions. And here I have the uniform strain response. And on this other side, I have on the usual polarization operator, which is the response to a uniform A, and some wave function, first order wave function, which is unknown, which is the complexity of the whole problem. So in principle, by deriving this formula, I have something that is not really desirable, which is the need for computing the response to a strain gradient, which I actually do not want to do. So we go back a little bit and recall that there is a variational principle in density functional perturbation theory, in that I can write the second order derivatives of the total energy as a variational functional of some parameter, of the first order wave functions. And here, well, we have a functional that is variational in the first order wave functions, and it depends parametrically on Q. So what I did essentially is to apply the 2n+1 theorem, which in this case is just simple Hellman-Feynman theorem, to this new perturbation expansion in Q, which is done on top already on a functional that is a perturbation expansion with respect to the acoustic phonon and electric field. The result is summarized here. So we have the second order energy can be written as a stationary function of the first order wave functions, and as a consequence we can calculate the clamped ion flexoelectric tensor by just combining operators and response functions at Q equals 0 that are already implemented in Aminit. We do not need to implement a new response function. We do not need to calculate gradients explicitly. And just to give you a flavor of the kind of formulas that comes out, here is an example. Looks very complicated, but actually we have some objects that are quite well known. The response to a uniform electric field here. Here we have the response to a uniform strain. Then we have this funny object, which is the response to the gradient of an A field. And then we have some other objects that are known, like the velocity operator of the gradients of the band projectors, all stuff that we know how to calculate and is already present in the code. So you might wonder why this funny response to an orbital B field came out in the context of flexoelectricity. How can the let's say the magnetic susceptibility enter a physical property that is so completely different, like the polarization response to a uniform to a strain gradient? So just to give you a flavor of some basic physics, let me give you this hand-waving argument. It's not hand-waving, actually. There are some fundamental grounds to it, but it's a sort of a bit of a simplified view. So imagine that you have a square sample, and you just start rotating it, a uniform rotation. So a uniform rotation, because of Coriolis force, produces in the electron some dynamical evolution and some surface currents that are actually equivalent to the surface currents I would have in a uniform applied B field. And this is a sort of version of the Larmor theorem. Now, think of producing a strain gradient in a sample, and just for simplicity, I break it down in pieces. And every piece, you see, apart from a strain, it has also a local rotation. And if you integrate in time the local rotation from the time 0 to the final time when the sample is deformed, you get that the current density at the surface will give a surface polarization, which is circulating. And if you sum up everything by bringing the sample back together, you see that there are some bulk, a macroscopic bulk polarization that emerges from this mechanism, which will be proportional to the susceptibility, magnetic susceptibility tensor of the material. But actually, there are also some surface contributions. So these are circulating currents, so they don't accumulate charge. This is a divergenceless field, so we actually do not need to care about it in the context of flexoelectricity when we measure an electrical signal, because this never accumulates charge anywhere in the sample. But it is something that physically, in principle, is real. Okay, now the numerical results. It took about a year to implement all these matrix elements, but in the end, the result is quite nice. For the first testing, we limited ourselves to cubic materials just because instead of 54 components, we have just 3. The flexoelectric tensor has just the longitudinal, the transverse, and the shear component. And these are the results for silicon and strontium titanate that we got with this analytic spatial dispersion technology compared with previous results that were obtained reference 26 is about doing a numerical derivative of the polarization at finite q. And this earlier work of mine, I'm actually quite happy that it turned out to be right, just because the methods were not quite mature, let's say, at the time. So it's good to see that it worked. Anyway, the agreement, as you see, is fantastic. So we can say that the implementation works very well. So I talked to you about the electronic components, but it's good to worry about the other contributions, just because lattice-mediated contributions are expected to be very large in materials that have a soft mode. And these are what people are mostly interested in these days. So the full flexoelectric tensor reads like this. We have some lattice-mediated term, electronic, and a funny mixed term, where we have some, well, this we already know how to calculate. And then in this other part, we have some known objects, like the internal piezoelectric strain response and the Born dynamical charges. But we also have some objects that are not quite familiar, like this P1 tensor, the dispersion of the Born dynamical charges, which consists in quadruples and a sort of geometric magnetization response. And then we have an internal strain that comes from the strain gradients. So good news is that we don't need to do everything all over again with the same technology. Just by replacing, shuffling around the combination of the perturbation and response we're looking at, we can calculate all these pieces just as easily and plug them into an DDB and just take a material and get the full flexoelectric tensor out of ab init, just as you get the full piezoelectric tensor so far. There are also, as I said, other properties that we are currently implementing, which is the other two combinations that are missing here, like electric field and electric field, and this would be the natural optical activity tensor. And then we have metric wave, which is the acoustical activity. I don't know if anybody's interested in the acoustical activity these days, but it might be nice to have it implemented for completeness. So, okay, let me go. This is what I just said, that the polarization response to a phonon has a dipolar part at q equals 0, and then a quadrupolar and a sort of magnetic-like response. I'll finish at first order in Q. And let me focus a bit on the quadruples, which have some interest for two reasons. One is lattice dynamics, in the sense that they give a contribution to the long-range forces that decays like 1 over the 4th power of the distance. This is weaker than the dipole-dipole interaction, but still is not negligible. It's still polynomial. And interestingly, we have this this seminal paper by Richard Martin in '72 that I don't know how he did, but he got a formula that relates the quadruples to the piezoelectric tensor. And indeed, I think we got probably the first numerical proof that this formula actually is fantastic. It works very well. So we calculated the quadruples in tetragonal lead titanate, and we got precisely the same piezoelectric tensor. But okay, quadruples, why? They can be important for lattice dynamics, I have said, and they are related to the piezoelectric tensor. So let's look at the piezoelectric and the dispersion of the phonon branches. And we took rhombohedral barium titanate as an example. And this is what we got. So if we take the standard ab init implementation or any code that does just the dipole-dipole, the treatment of the dipole-dipole interaction in the Fourier interpolation of the band structure, you get the red line. So there is an imaginary branch here that would mean that you have a ferroelastic instability, but you don't, because this is the ground state structure. And once we take the dipole-quadrupole interaction into account in the Fourier interpolation, this artifact disappears nicely, and we get a band structure that converges very fast as a function of the coarse Q mesh. Over here we have convergence tests. I don't, well, the message is clear, and then let me go to the conclusions, and I leave it there, and thank you for your attention.
So thank you very much for the very nice presentation.
Thank you.
So presentation is open for questions.
Very beautiful work. Now, you are calculating bulk properties, but you are saying this is going to be very important at the nanoscale, where actually surface dominates over the bulk. Do you have any sense then that actually maybe all of this is going to be masked by what happens at the surfaces?
This is an excellent question, and I'm very happy that you asked it, because this time I haven't had time to go through to the main basics of flexoelectricity, but actually there are surface contributions to flexoelectricity that I didn't discuss in my talk today. And these are certainly important at the nanoscale, but the funny thing is that these surface contributions in the case of flexoelectricity are important at any scale. So I did a calculation a few years ago where I calculated the full flexoelectric coefficient, including surface terms and all relaxations, etc., for strontium titanate, by taking a strontium oxide terminated surface and a titanium dioxide terminated surface, and I got an opposite sign. So, which means that at any size, even macroscopic thicknesses, just by switching the layer of atoms at the surface, you can get an opposite sign of the flexoelectric response. So this is probably not good news if you're doing experiment and try to make a sense of them. Yeah, dispersion properties are delicate with the surfaces because dispersion is the real space moment of something. And so when you take the real space moment, whatever you have at the boundary becomes large.
You didn't say anything or very little about self-consistency effect. That is, whenever you have a longitudinal phone, you have a depolarization field and the like. So in the standard, the FPT, of course, is taken care automatically, but how in the other complicated terms? So in a very old paper of yours, a very elegant one with the metric, and you mentioned the covalent form of Poisson equation and the like. How does this enter in this formulation?
Yes, also a very good question. So self-consistency is fully taken into account. So I have here a formula that I can show you. So this is the full functional, let's say, at finite Q. And then what you do is that you have a self-consistent part and something that depends only on external potentials. And the way the self-consistency is taken into account is by deriving in Q these objects, which are the densities and the Poisson kernel, the Coulomb kernel. So in practice, I believe that in this approach, which is based on an analytic derivation in Q of the functional, the curvilinear electrostatics that you mentioned translates into a gradient of the Coulomb kernel.
I found also extremely interesting your rhombohedral phonons, and I just wanted to understand exactly what you did there. So it's, did you change the non-analytic term to add the quadrupoles?
Yeah, exactly. So we wrote, just like the dipole-dipole interaction, we wrote the next term in Q which is the dipole-quadrupole interaction. It is something that tends to 0, of course, at gamma, so it is not strongly analytic at gamma as the dipole-dipole is. But it is non-analytic at first order in Q. So this produces trouble if you want to calculate the elastic constants, for example. So if you want to have a reliable sound velocity out of your phonon branches, which might be quite crucial, as we've seen in previous talks, for calculation of thermal properties, for example, then you must really think of taking care of these long-range forces. Here, we went all the way to quadrupole and dipole-octupole, and also we calculated the dispersion of the dielectric constant to see how it goes at the next level. And, well, it seems that you need to be correct all the way to second order in Q if you want to be safe with your velocities.
So this is a very general and very important result, no?
I think so. I think so. Yeah, the quadruples were sort of a byproduct of the calculation that we used as a first step to test our ideas and our ability to implement things in Abinit. But in the end, I think they are not so trivial. We are working on many applications also with Xavier, and I think it's nice to have them out of Abinit. And it's really at no cost, because you don't need to do an additional calculation with respect to those that you have already, like the phonons, the uniform electric field, and the Q derivatives of your ground state wave functions.
Okay, so I'm afraid we have to move on. So let's thank Massimiliano again.